This is Optimization Series second video. In this video we learn about mathematic optimization. Optimization problems in mathematics have emerged since ancient times, with the establishment and development of mathematics. The historical term mathematical programming, widely synonymous with optimization, is a collection of mathematical principles and methods used to solve quantitative problems in many fields. The first known use of optimization was in 1857. When most used word, linear programming was proposed by George Dantzig in 1947, based on the work of three Nobel laureate economists, Vasily Leontief, Leonid Kantrovich, Schilling Koopmans. Okay, let's discuss in detail about mathematic optimization. Optimization indicates the very big area of problem. Normally we divide these problems with their linear and nonlinear nature. The inequality constraints allow linear problem models to capture the discrete nature of some decisions. For example, a binary variable with bounded values can be used to decide whether to perform some action, which is a mixed integer linear problem. A MIP model with a quadratic objective is called a mixed integer quadratic programming (MIQP) problem. More detail we will continue to explain the linear and nonlinear programming in next slides. In mathematics, linear programming is a method of optimizing operations with some constraints. The main objective of linear programming is to maximize or minimize the numerical value. It consists of linear functions, which are subjected to the constraints in the form of linear equations or in the form of inequalities. An integer program is obtained by taking a linear program and adding the condition that a non-empty subset of the variables be required to take integer values. When all variables are required to take integer values, the integer program is called a pure integer program, otherwise it is called a mixed integer program. Models without any quadratic features are often referred to as mixed integer linear programming, MILP, problems. Where variable whose values are restricted to 0 or 1, called a binary variable, can be used to decide whether or not some action is taken. In general, mathematic optimization indicate the linear programming. Let's continue the nonlinear. An optimization problem is nonlinear if the objective function maximize, z, or any of the inequality constraints cost of x1 less than or equal to 0. Where I equals 1, 2, m, or equality constraints cost of x2 equals 0. Where j equals 1, 2, n, are nonlinear functions of the vector of variables x1 and x2. For example, if constraints contains the components x1 and x2, then the function 3 plus 2, x1 minus 7, x2 is linear, whereas the functions x1, cube plus 2x, square and 3, x1 plus 2, x1 with x2 plus x2 are nonlinear. Models with any quadratic features are often referred to as mixed integer quadratic programming, MIQP, problems. Another special case is quadratic programming, in which the constraints are linear but the objective function is quadratic. That is, it contains terms that are multiples of the product of two variables. For instance, the function 3x1, square plus 1.4, x1 with x2 plus 2, x2, square is a quadratic function of x1 and x2. Another useful way to classify nonlinear problems is according to the number of variables, that is, components of x. From the beginning, we learned about different types of programming. Here we discuss the difference between linear and nonlinear equations. Their differences are explained here with definitions and examples. Linear forms a straight line or represents the equation for the straight line. Where nonlinear does not form a straight line but forms a curve. Linear has only one degree. Or we can also define it as an equation having the maximum degree 1. But nonlinear equation has the degree as 2 or more than 2, but not less than 2. Linear equations form a straight line in xy-plane. These lines can be extended to any direction but in a straight form. But nonlinear forms a curve, and if we increase the value of the degree, the curvature of the graph increases. The general representation of linear equation is y equals mx plus c. Where x and y are the variables, m is the slope of the line and c is a constant value. The general representation of nonlinear equations is x square plus by, square equals c. Where x and y are the variables and a, b and c are the constant values. Here we discuss about components of mathematical programming. Mainly optimization components are divided into three parts. First one is decision variables. For example, x1, x2, x1, x2 are variables of optimization programming. Second component is objective function, maximize z, equals 10, x1 plus 20, x2. Here we solve the problem to maximize the z. Third component is constraints, for example x1 less than or equal to 8, x2 less than or equal to 20, x1 plus 4, x2 less than or equal to 120, x1 greater than or equal to 0, x2 greater than or equal to 0, are non-negativity constraints. In detail we will follow the latter parts. A decision variable is optimization part of an optimization problem. It has a domain, which is a compact representation of the set of all possible values for the variable. Decision variable types are references to objects whose exact nature depends on the underlying optimizer of a model. A decision variable can be instantiated only in the context of a given model instance. The purpose of an optimization model is to find values for the decision variables, such that all constraints are satisfied, or, in optimization problems, to find values for the variables that satisfy all constraints and optimize a specific objective function. A decision variable declaration in optimization specifies the type and set of possible values for the variable. Once again, decision variables can be of different types, integer, float, and it is possible to define multidimensional arrays of decision variables. Objective function is prominently used to represent and solve the optimization problems. The objective function is of the form z equals 10, x1 plus 20, x2, where x1, x2 are the decision variables. The function z equals 10, x1 plus 20, x2 is to be maximized or minimized to find the optimal solution. Here the objective function is governed by the constraints x1 greater than or equal to 0, x2 greater than or equal to 0. The optimization problems which needs to maximize the profit, minimize the cost, or minimize the use of resources, makes use of an objective function. When z has an optimal value, maximum or minimum, where the variables x1 and x2 are subject to constraints described by linear inequalities, this optimal value must occur at a corner point, vertex, of the feasible region. Let R be the feasible region for a linear programming problem, and let z equals 10, x1 plus 20, x2 be the objective function. If R is bounded, then the objective function z has both a maximum and a minimum value on R, and each of these occurs at a corner point, vertex, of R. A constraint defines one or more expressions that place limits on the feasible values of variables. Constraints differ from objectives in that the expressions include relationships, equalities or inequalities. While objectives can be indexed, this feature is infrequently used. In contrast, constraints are commonly indexed, allowing for a collection of related constraint expressions to be constructed and stored in a single constraint object. Inequality constraints have the form expression 1 less than or equal to expression 2, or expression 1 greater than or equal to expression 2, where expression 1 and expression 2 may be non-constant expressions. Note that less than and greater than are not supported. Equality constraints have the form expression 1 equals expression 2, where expression 1 and expression 2 may be non-constant expressions. Range constraints have the form lower less than equals expression 1 less than equals upper, where lower and upper are constant expressions and expression 1 is a non-constant expression. Next video we will start using codes to explain the linear programming and phrases that we used in this video. So please keep watching.